That point of absolute darkness holds secrets that could rewrite the laws of physics. We are on the verge of discoveries that challenge our most fundamental ideas about space, time, and reality itself. By the end of this exploration, you will know 25 of the most incredible theories about black holes that could actually be true. We will investigate if these cosmic giants are gateways to other universes and what truly happens to everything they consume. What do you believe lies beyond the event horizon? The crushing grip of a black hole seems to offer only one destination: oblivion. But what if that is merely an illusion, a cosmic curtain hiding a passage far stranger than destruction? The first theory proposes that black holes are not endpoints at all, but gateways. Within the heart of a black hole, where our understanding of physics breaks down, the singularity might not be a final crushing point. Instead, it could be a tunnel, a theoretical structure known as an Einstein-Rosen bridge, connecting two distant points in spacetime. Think of the fabric of the universe as a simple sheet of paper. If you want to get from one side to the other, the long way is to travel across the entire surface. But if you could fold the paper, piercing through to connect the 2 points directly, you create a shortcut. A wormhole is that shortcut. The immense gravity of a black hole could be warping spacetime so severely that it punches such a tunnel into existence, potentially leading to another universe entirely or a different time and place in our own. The challenge, and it is a monumental one, is traversability. Could anything actually survive the journey? The forces at the center are so extreme that the tunnel might be unstable, collapsing instantly. Or it might be filled with violent radiation and energy that would shred any object into its most fundamental particles. The gateway may exist, but the price of passage could be annihilation, leaving us to wonder if these cosmic doors are simply one-way trips into the unknown. A gateway that annihilates everything trying to pass through seems like a permanent, indestructible prison. Yet Stephen Hawking proposed an idea so radical it suggests even black holes have a finite life. His theory states that black holes are not truly black. They glow, they radiate, and over eons they can fade away entirely. This phenomenon is known as Hawking radiation. It arises from the bizarre and unpredictable nature of the quantum realm, right at the edge of the event horizon. In what we think of as empty space, pairs of virtual particles constantly flicker in and out of existence. Usually, these particle pairs annihilate each other almost instantly, but at the precipice of a black hole, something extraordinary can happen. One particle of the pair might fall across the event horizon while the other escapes into space. The particle that escapes becomes real radiation, carrying away a tiny amount of the black hole's energy. To balance the cosmic books, the black hole loses a corresponding amount of mass. This process is incredibly slow for a large black hole. A black hole with the mass of our Sun would take trillions upon trillions of years to evaporate even a fraction of its mass. But for the smallest theoretical black holes, the evaporation could be rapid and dramatic, ending in a final, powerful burst of energy. This gentle, quantum whisper of radiation forces us to completely rethink the fate of these cosmic giants. They are not eternal, they live, and given enough time, they die. Hawking's fading giants introduce a deeper mystery, one that strikes at the very heart of reality. If a black hole can evaporate completely, what happens to all the information about the things it swallowed? Every star, every planet, every atom that ever crossed the event horizon carried with it a unique blueprint, a specific arrangement of particles and properties. According to the unbreakable rules of quantum mechanics, that information can never be truly destroyed. It might be scrambled beyond recognition, but it must, in principle, be recoverable. This creates a fundamental conflict with Einstein's general relativity, which describes the black hole's interior. From that perspective, anything that falls in is irretrievably lost, crushed into the singularity, and erased from our universe. The black hole itself is defined only by its mass, charge, and spin. It retains no memory of whether it formed from a collapsed star or a billion library books. This is the information paradox, a direct clash between our two most successful theories of the universe. How can both be true? One proposed solution is as beautiful as it is bizarre, the holographic principle. It suggests that all the information about what falls into a black hole is not lost inside. Instead, it is encoded like a cosmic hologram on the two-dimensional surface of the event horizon. Think of it like watching a movie on a flat screen. The image appears to have depth and volume, but every bit of data that creates that three-dimensional illusion is actually stored on the two-dimensional screen itself. In this view, the event horizon is that screen. It holds a perfect, if incredibly complex, record of everything that has ever fallen in. As the black hole evaporates through Hawking radiation, this information is slowly and carefully released back into the universe, preserving the quantum rulebook. The three-dimensional space within the black hole is then an emergent projection, a reality generated from that two-dimensional data. This implies that our own universe, with its rich three-dimensional appearance, might itself be a holographic projection from a distant two-dimensional surface. The paradox forces us to ask, is the world we perceive merely a shadow of a deeper, more fundamental reality written on the boundary of space itself? If the holographic principle suggests information is not destroyed but merely transformed, then perhaps the matter that falls into a black hole is not destroyed either, only transported. This leads us to a theory that feels like pure science fiction, the existence of white holes. If a black hole is a one-way street where everything enters and nothing returns, a white hole is its theoretical opposite, a cosmic exit door from which matter and energy can only pour out. Nothing from our universe can ever cross into a white hole. Its event horizon is an impenetrable boundary pushing everything away. The mathematics of Einstein's general relativity, the very same equations that predict black holes, also allow for this strange solution. They are two sides of the same coin, connected by the theoretical tunnel of a wormhole. Where a black hole's gravity pulls everything inward toward the singularity, a white hole would have a singularity in its past, violently expelling everything in its history outward into the universe. This presents a fascinating possibility. What if everything that is drawn into a black hole in our universe is violently spewed out of a white hole in another universe, or even in a different part of our own? The cosmic ledger would be balanced, with matter and energy being recycled on an unimaginable scale. The most profound speculation connects this idea to the very beginning of everything. Some physicists have proposed that our own Big Bang, the immense explosion of energy and spacetime that created our cosmos, could have been the ultimate white hole event, a singularity erupting into a new reality. This paints a picture of a vast cosmic cycle, where universes are born from the death cries of black holes in another realm entirely. While no white hole has ever been observed, their possibility lingers in the equations, a ghostly reminder that our universe might be just one chamber in an infinite, breathing cosmos. While most black holes are born from the violent deaths of massive stars, there is another, more ancient possibility. The universe's very first black holes might have been forged in the chaotic furnace of the Big Bang itself. These are known as primordial black holes, and they are fundamentally different from their stellar cousins. They did not need a star to collapse. Instead, they could have formed from the immense pressures and densities that existed in the first fleeting moments after creation, when the fabric of spacetime was a seething, turbulent sea. A region of space just slightly denser than its surroundings could have collapsed under its own gravity, pinching off into a tiny, profound darkness. This means they could be almost any size, from as small as a single atom to larger than a planet. Their tiny size, however, is where the theory gets truly fascinating, because it offers a potential solution to one of cosmology's greatest mysteries, dark matter. We know dark matter exists because we can see its powerful gravitational pull on galaxies, holding them together, yet it emits no light and remains completely invisible. Primordial black holes, especially those with the mass of a large asteroid or a small planet, could be the perfect candidate. Trillions of them could be drifting unseen throughout the galaxy, their collective gravity influencing the motion of stars, yet being far too small and dark for our telescopes to spot directly. How could we ever find such a ghostly presence? One way is through their gravitational effects. As a primordial black hole passes between us and a distant star, its gravity would act like a lens, bending the starlight and causing the star to temporarily brighten, a phenomenon called microlensing. We have seen these events, and while they could be caused by other faint objects, primordial black holes remain a compelling suspect. The other clue lies in their eventual end. The smallest of these ancient black holes, those with the mass of a mountain but compressed into a space smaller than a proton, would be radiating away their energy through Hawking radiation. Their final moments would not be a slow fade but a spectacular high-energy explosion. We have yet to detect such a definitive burst, but the search continues, hunting for the last dying breaths of the universe's oldest ghosts. But the idea of a singularity, a point of infinite density, has always been a sign that our physics has reached its breaking point. String theory offers a radical escape from this mathematical dead end. It proposes that the heart of a black hole is not a terrifying, dimensionless point, but something far stranger, a fuzzball. Imagine the very fabric of space is woven from unimaginably tiny, vibrating strings. In a black hole, these strings would not collapse to a single point. Instead, they would stretch and tangle together into a vast, complex ball that fills the entire region inside the event horizon. This is the fuzzball, a dense, fuzzy knot of fundamental strings with no sharp boundary or central singularity. Its surface is the event horizon we observe from the outside. This single idea could solve two of the biggest problems with black holes at once. First, it completely eliminates the paradox of the singularity, that nonsensical point of infinite density where the laws of physics simply give up. In the fuzzball picture, there is no such place. The interior is a busy, structured mess of quantum strings, not an empty pit leading to a mathematical absurdity. Second, and perhaps more profoundly, it offers a clear solution to the information paradox. Remember the problem of what happens to the information of things that fall in. If a black hole is a fuzzball, the information is not lost behind a featureless horizon. It is stored in the specific, intricate way those strings are tangled and vibrating within the fuzzball itself. When the black hole evaporates via Hawking radiation, that radiation can carry away the information encoded in those vibrations, preserving the quantum rulebook perfectly. The information never gets trapped or destroyed. It is merely transferred into a new, incredibly complex form. While we cannot yet peer inside a black hole to confirm this, the fuzzball theory provides a compelling, self-consistent picture where the terrifying unknown is replaced by a complex quantum reality. These ancient cosmic remnants might be the invisible architects of our universe. When we look at a galaxy, we see stars and gas swirling at incredible speeds, moving so fast that they should fly apart. They do not because something we cannot see, a mysterious form of matter, holds them together with its gravity. This is dark matter, and primordial black holes could be its hidden form. The beauty of this idea lies in its simplicity. We know these black holes could have formed in the early universe, and they would be naturally dark, emitting no light. The question becomes one of numbers and mass. What size would they need to be to account for the vast gravitational effects we observe? Scientists have explored a wide range, from black holes as massive as a planet to ones as light as an asteroid. If trillions of these objects, each with the mass of a small moon, were drifting unseen through galactic halos, their collective gravity would perfectly explain how galaxies are bound together. But how do you find something that gives off no light? The primary method is to watch for their ghostly influence on the light from distant stars. This is the hunt for gravitational microlensing. Imagine a primordial black hole drifting silently through space. If it passes directly between our telescope and a faraway star, its gravity will act as a tiny lens, bending and focusing the starlight. For a brief period, that distant star will appear to temporarily brighten, then fade back to normal as the black hole moves on. Our telescopes have recorded thousands of these mysterious brightening events. While some are caused by faint stars or other objects, a population of primordial black holes remains a prime suspect to explain many of them. This cosmic hide-and-seek is one of the most active frontiers in astronomy, a patient search for the subtle shadows of these ancient giants, whose silent gravity may be the very framework upon which galaxies are built. This serene passage through the event horizon, however, is now being challenged by a truly terrifying idea. The firewall paradox suggests that the boundary of a black hole is not a quiet, invisible line, but a blistering wall of fire. An astronaut crossing the horizon would not experience a gentle fall into the unknown. They would be instantly incinerated by a searing curtain of high-energy radiation. This shocking concept did not emerge from nowhere. It is a direct and deeply controversial consequence of the struggle to solve the information paradox. For information to be preserved as a black hole evaporates as quantum mechanics demands, something dramatic must happen at the event horizon. The theory proposes that the quantum entanglement of particles at the very edge is violently broken, releasing an immense burst of energy. This creates the firewall, a destructive barrier that protects the laws of quantum physics but at a great cost. The problem is that this firewall fundamentally contradicts Einstein's principle of equivalence, a cornerstone of general relativity. This principle assures us that an observer in free fall should not feel any special effects as they cross the event horizon. They should experience nothing out of the ordinary, at least until the tidal forces much later tear them apart. The firewall shatters this elegant idea, placing a very tangible, violent structure at a location that relativity says should be empty space, so we are left with a profound dilemma. Do we accept the firewall and abandon a core principle of Einstein's theory, a principle that has been tested and confirmed for a century? Or do we reject the firewall and risk violating the fundamental quantum law that information cannot be destroyed? The paradox forces us to question the very nature of the boundary around a black hole. Is it a quiet point of no return, or is it the most energetic and deadly place in the entire universe? The serene emptiness of the event horizon, a clean slate defined by only 3 numbers, is a powerful and elegant idea. But it may be an illusion. The classical no-hair theorem insists that a black hole is the ultimate simple object stripped of all complexity. Its mass, its electric charge, and its spin are all you need to know. It forgets whether it was born from a star made of hydrogen or iron, or if it ever swallowed an entire solar system. All that intricate information is seemingly lost forever. Yet, the information paradox tells us this cosmic amnesia cannot be the final answer. Something must remember. This is where a remarkable new idea emerges, one that gives black holes what physicists poetically call hair. This is not literal hair, of course, but a metaphor for additional, subtle qualities that could be imprinted on a black hole's event horizon. These quantum hairs would be tiny distortions in the fabric of spacetime itself, wrinkles and ripples created by the specific properties of everything that has ever fallen in. Think of it like the surface of a pond. If you toss a single, smooth stone into the water, the ripples it creates are simple and predictable. This is like a black hole with only mass, charge, and spin. But if you throw in a handful of gravel, each piece with its own unique shape and size, the resulting pattern on the water's surface becomes incredibly complex and detailed. The quantum hairs are that complex pattern. Each piece of matter that crosses the event horizon would leave its own faint gravitational fingerprint, a permanent record etched into the very boundary of the black hole. This information would not be hidden deep inside, but displayed for the universe to see, encoded in the subtle geometry of the horizon. The radiation slowly leaking from the black hole could then carry this information away, resolving the paradox. The black hole is not bald after all. It wears a crown of intricate quantum hair, each strand a story of what was lost, ensuring that no memory in the universe is ever truly erased. This intricate quantum hair, however, is not the only challenge to the classic image of a black hole. An even more radical idea suggests that black holes, as we traditionally define them, might not exist at all. In their place could be objects called gravastars, cosmic mirages that look like black holes from the outside, but hide a completely different reality within. A gravastar would possess the same immense gravitational pull, capable of bending light and trapping it in orbit, but there the similarity ends. It would have no event horizon, no point of no return. And most importantly, it would contain no singularity. Instead, a gravastar is envisioned as a kind of cosmic bubble. Its interior is a vast, empty void filled with a mysterious repulsive force known as dark energy, the same force that is causing the expansion of our entire universe to accelerate. Containing this exotic interior is an incredibly thin, ultra-dense shell of matter, a crust that is likely only a few trillionths of a meter thick, yet is tougher than any material we can conceive. This shell is what we would mistake for the event horizon. You could, in theory, cross this boundary, but you would not be crushed into nothingness. You would simply find yourself inside this strange, dark energy-filled space, a realm of negative pressure that would likely push you right back out. The implications are profound. A gravastar would solve both the information paradox and the problem of the singularity in one elegant stroke. Since there is no true event horizon, information never gets permanently trapped. It can, in some form, escape or be reflected. And with no point of infinite density, the laws of physics remain intact and unbroken throughout the entire structure. The universe would not need to invent new rules to describe its most extreme objects. While gravastars remain entirely theoretical, their possibility forces us to question what we are truly seeing when we observe these dark giants in the cosmos. Are we looking at bottomless pits of destruction, or are we seeing the most durable containers in existence, holding back a universe of nothingness? The very structure of a gravastar hints that reality might be far more flexible than we ever believed. This flexibility reaches its ultimate expression in one of the most mind-bending proposals of all, that black holes could function as natural time machines. The key to this possibility lies with a specific type of black hole, one that is spinning at a significant fraction of the speed of light. This is known as a Kerr black hole, and its rotation does something extraordinary to the fabric of spacetime itself. It drags the very continuum around with it like a spinning spoon stirring a thick fluid. This effect, called frame dragging, becomes so intense near the black hole that it could warp the paths that objects can take through time. According to certain solutions of Einstein's equations, this warping could theoretically create what physicists call a closed time-like curve. This is a path through spacetime that loops back on itself, allowing an object to return to its own past. Imagine drawing a line on a piece of paper to represent your journey through time, always moving forward. A closed time-like curve would be like rolling that paper into a cylinder, so the line eventually meets its own beginning. An astronaut traveling on such a path would, from their own perspective, be moving forward normally, but from the outside, they would be arriving at a point in time before they even left. The potential gateway to such a path is thought to exist inside the inner event horizon of a rotating Kerr black hole, in a region known as the ergosphere, where the twisting of spacetime becomes so severe that the normal flow of time breaks down. Yet the practical challenges are as immense as the theoretical ones. To even reach this region, you would first have to survive the passage through the outer event horizon and navigate the chaotic forces within. Furthermore, the existence of closed time-like curves creates immediate and profound paradoxes. The most famous is the grandfather paradox. What if you traveled back in time and prevented your own grandfather from meeting your grandmother? This would create a logical inconsistency, a loop where you could never have been born to go back in time in the first place. Physics has proposed potential resolutions, such as the idea that any action you took in the past was always a part of history, or that the timeline would simply split into a new parallel universe. But the very fact that our most fundamental equations allow for such a staggering possibility forces us to confront a deep question. Is time travel a mere fiction, or is it a genuine, though perhaps unreachable, feature of the cosmos, hidden within the most violent and twisted regions of spacetime? The profound link between wormholes and entanglement offers a breathtaking bridge between our two most powerful yet conflicting theories of reality. This is the ER equals EPR conjecture, an idea that connects the geometry of spacetime to the ghostly bonds of the quantum world. The ER stands for Einstein-Rosen bridges, the formal name for wormholes, those hypothetical tunnels through spacetime. The EPR stands for the Einstein-Podolsky-Rosen paradox, a famous thought experiment that first highlighted the bizarre nature of quantum entanglement. For decades, these two ideas lived in separate scientific kingdoms, one governed by gravity and the grand geometry of general relativity, the other by the probabilistic rules of quantum mechanics. The ER equals EPR conjecture boldly proposes they are not just similar, they are two different descriptions of the exact same thing. Imagine two black holes that have become mysteriously entangled. From the perspective of quantum mechanics, they are linked by an invisible, instantaneous connection. No matter how far apart they are separated, measuring the properties of one instantly influences the other, a phenomenon Einstein famously called spooky action at a distance. Now view this same pair through the lens of general relativity. The conjecture suggests that this spooky quantum connection is physically manifested as a microscopic wormhole, a tiny ER bridge connecting the interiors of the two black holes. The entanglement is the wormhole, and the wormhole is the entanglement. This is not a tunnel you could ever travel through. It is unimaginably small, likely existing at the Planck scale, far smaller than an atom. Its significance, however, is cosmic. It provides a geometric picture for how quantum information can be shared across vast distances without violating the speed of light. The information does not travel through space, it takes a shortcut through the wormhole that the entanglement itself creates. This radical idea suggests that the fabric of spacetime itself, the very stage upon which the universe plays out, may be woven from a vast, dense network of quantum entanglement. Every connection between particles might be supported by an unimaginably tiny thread in the geometry of reality, hinting that the universe is not just connected but fundamentally one. The boundary between a neutron star and a black hole is not as sharp as we once believed. Deep within the cosmic graveyard, there may exist strange hybrid objects that blur this line entirely. A neutron star is the collapsed core of a massive star, so incredibly dense that a single teaspoon of its material would weigh billions of tons. It is held up from total collapse by a powerful quantum force, a fierce outward pressure from its constituent neutrons. But what if a star is just a little too massive to form a stable neutron star, yet not quite massive enough to immediately collapse into a black hole? This could lead to the birth of an exotic transitional object. One theoretical possibility is the quark star, where the immense pressure breaks down the neutrons themselves, creating a soup of free quarks, the fundamental building blocks of all matter. This quark-gluon plasma would be even denser and stranger than a neutron star. Another, even more speculative idea is the electroweak star, where at its very core the forces of electromagnetism and the weak nuclear force temporarily unite, generating enough outward pressure to stave off collapse for a few million years. These objects would look very much like black holes from a distance, possessing intense gravity and possibly even an accretion disk of hot gas. They would be cosmic masqueraders, dark remnants hiding their true, bizarre nature. The key to unmasking them lies in the way they vibrate. When two such ultra-dense objects collide, they send ripples through space-time itself. Gravitational wave observatories are now our most powerful tool for studying these events. The specific frequency and decay of these ripples, the ring-down of the newly formed object, acts like a unique fingerprint. A pure black hole has a very clean, predictable gravitational wave signature as it settles into a calm state. A hybrid object, however, would ring differently. Its complex internal structure and lack of a true event horizon would produce subtle distortions in the signal, a kind of cosmic echo that betrays its true identity. As we collect more data from collisions across the universe, we are beginning to listen for these telltale whispers, searching for the vibrations of something that is neither truly a star nor a hole, but a ghost in between. The intricate dance of information on a black hole's surface leads to an even more profound possibility. What if the event horizon is not merely a storage device, but a processor, a cosmic engine performing calculations of unimaginable complexity? This speculative theory proposes that a black hole is in essence a natural quantum computer. The fundamental unit of this computer would be the Planck area, the smallest possible patch of space, a trillionth of a trillionth the size of a proton. The entire surface of the event horizon could be thought of as a vast mosaic of these tiny pixels, each one capable of storing a single bit of quantum information. But this is not a static hard drive. The chaotic, dynamic interactions at the horizon, the constant influx of new matter, and the slow leak of Hawking radiation could be seen as the computer's operations. It is constantly updating, processing, and transforming the information of everything it consumes. This processing power would be beyond any technology we could ever build. A single black hole could be performing more calculations each second than all the computers on Earth have performed in their entire history. This idea finds a beautiful synergy with the holographic principle. If our three-dimensional reality is a projection from a two-dimensional surface, then the universe itself might be the output of a cosmic computation running on the boundary of space. The laws of physics we observe, from the motion of planets to the fusion in stars, could be the emergent result of this underlying information processing. A falling star would not be simply destroyed. Its information would be uploaded and integrated into the most powerful processing network in existence. The black hole is not a mindless shredder, but a transcendent machine, translating the physical world into a language of pure information and computing the next state of reality itself. We are left to wonder if we, too, are part of this vast calculation, living in a universe being continuously computed on the edge of a void. This holographic view of reality might be the key to unlocking the universe's deepest operating system. The holographic principle takes the strange idea of information storage on a black hole's surface and expands it to a cosmic scale. It proposes that all the information needed to describe everything within a three-dimensional volume, every star, every atom, every speck of dust, is not contained within that space in the way we intuitively think. Instead, it is encoded like a perfect hologram on the two-dimensional boundary surrounding that volume. A black hole is the ultimate proof of concept. Its event horizon is that boundary. The information about everything that has ever fallen into the black hole is not lost inside the vast three-dimensional interior. It is painted in an incredibly complex code onto the two-dimensional surface of the horizon itself. This is why the information content of a black hole is proportional to its surface area, not its volume. Adding more volume to a black hole increases its surface area, and it is that growing surface that stores the new data. To understand this, think of a holographic sticker on your credit card. The image has depth and appears three-dimensional, but every bit of data that creates that illusion is stored on the flat, two-dimensional sticker. The event horizon is that sticker for the entire interior of the black hole. The three-dimensional space we associate with the black hole's interior is not the primary reality. It is an emergent phenomenon, a projection generated from the data on the surface. This principle might not stop at black holes. Our entire universe, with its immense three-dimensional expanse of galaxies and clusters, could itself be a holographic projection. The information for every particle, every force, and every event we experience could be encoded on a distant, two-dimensional surface at the edge of the cosmos. We are living inside the projection, unaware that the true reality is a vast cosmic film storing the data of existence. This suggests that the universe is fundamentally informational. What we perceive as matter and energy are simply the physical expressions of bits of data being processed on the ultimate screen. The solidity of the world around us, the vast distances between stars, all of it might be an incredibly convincing illusion, a cosmic shadow play generated from a simpler, flatter reality we cannot see. A gravitational singularity laid bare, stripped of its event horizon, would be the most terrifying and revealing object in the cosmos. This is the hypothetical naked singularity, a point of infinite density where the laws of physics break down, but one that is completely exposed to the universe. According to the cosmic censorship hypothesis proposed by Roger Penrose, nature abhors such a spectacle. It suggests that every singularity must be modestly cloaked behind an event horizon, hidden from our view to protect the causal order of the universe. This cosmic curtain ensures that the unpredictable, lawless insanity of the singularity cannot affect the orderly reality outside. But what if this hypothesis is wrong? What if, under the right conditions, a black hole could be stripped of its protective horizon? The most likely scenario involves a black hole spinning at the absolute maximum possible speed. If it gains just a little more angular momentum, perhaps from gobbling up a final, fast-rotating star, its centrifugal forces could overcome the immense inward pull of gravity. In this moment, the event horizon would theoretically vanish, popping like a bubble and leaving the raw singularity exposed for all to see. The implications would be as profound as they are frightening. Without an event horizon, we could, in principle, observe the singularity directly. We could see physics pushed to its absolute breaking point, a laboratory for quantum gravity playing out in real time. But this freedom comes at a great cost. A naked singularity would not respect our familiar flow of cause and effect. It could spew out information and radiation in unpredictable, chaotic bursts, potentially creating paradoxes where the future influences the past. The universe's orderly timeline could become tangled and frayed around this exposed wound in space-time. The hunt for these objects is a search for the ultimate rule breaker, a place where the universe's deepest secrets are no longer hidden in darkness, but screaming into the void for anyone brave enough to look. A black hole's long fade into nothing might not be its final act. That final burst of Hawking radiation could be the prelude to a cosmic rebirth, a transformation so violent it reverses the very nature of the object. This is the theory of black hole metamorphosis, where a dying black hole undergoes a quantum bounce and becomes its opposite, a white hole. The process begins with Hawking radiation slowly bleeding the black hole of its mass over eons. As it shrinks toward a microscopic size, quantum gravitational effects, normally negligible, become the dominant force. At this critical point, the relentless collapse dictated by gravity could be met with an equal and opposite quantum repulsion. Instead of crushing down to a final point of oblivion, the black hole would rebound. Think of it like compressing a spring with all your might. You can push it down, but at a certain point, the spring's inherent energy fights back, forcing it to expand again with tremendous force. In this scenario, the black hole is the spring and the quantum bounce is its release. The result would not be a gentle expansion but a catastrophic eruption. The newly formed white hole would violently expel all the energy and information the black hole had accumulated over its entire lifetime. It would be a cosmic reset button, a grand recycling of matter and energy on a quantum scale. This explosive transition would be brief, likely lasting only a fraction of a second, but unimaginably brilliant, potentially outshining an entire galaxy for that fleeting moment. This idea provides an elegant, if dramatic, solution to the information paradox. The information is not slowly leaked back into the universe in a garbled form through Hawking radiation. It is stored, preserved in the quantum structure of the remnant, and then released all at once in a final, definitive burst when the white hole forms. The black hole's life of consumption ends not with a whimper but with a transformative bang, seeding the cosmos with the raw materials for new possibilities. A black star offers a radical reinterpretation of what we see in the dark heart of a galaxy. This theoretical object forms just like a black hole from the collapse of a massive star, but it halts its collapse at the very last possible moment. It becomes incredibly dense and dark, bending light so severely that it traps photons in tight orbits, yet it never quite crosses the threshold to form a true event horizon. From a great distance, a black star would look identical to a black hole. It would have the same intense gravitational pull, the same shadowy silhouette against glowing background gas, and the same ability to capture light. The difference is not in its appearance but in its fundamental nature. A black hole, by definition, possesses that one-way door, the point of no return from which not even light can escape. A black star has no such door. Light can still escape from its surface, but the gravitational pull is so immense that the light loses nearly all its energy in the struggle to get away. Imagine a runner trying to sprint up an endlessly steep hill. They are moving forward, but they are expending all their energy just to make any progress at all, slowing to an exhausted crawl. The light leaving a black star is like that exhausted runner. It becomes stretched into the longest, weakest radio waves, carrying so little energy that it is practically undetectable across the vastness of space. This subtle distinction solves some of the most vexing problems in physics. Without an event horizon, there is no information paradox. The information about every atom that falls onto a black star is never truly trapped. It remains, in principle, retrievable from the altered light and radiation. Even if retrieving it is a monumental technological challenge, the terrifying firewall paradox also vanishes because there is no special boundary where the laws of physics suddenly change. An object falling toward a black star would experience a smooth, if increasingly violent, journey, never hitting a wall of fire. The black star stands as a compelling alternative, suggesting that the universe's darkest objects might not be bottomless pits, but merely the ultimate cosmic dead ends where light goes to fade but information never truly dies. Our own cosmic origin story might be written in the collapse of a star from another reality. This theory suggests that the Big Bang was not a singular beginning from nothing, but the violent birth of a white hole, the other end of a black hole tunnel from a parent universe. In that foreign cosmos, a massive star collapsed, its core condensing into a singularity and piercing the fabric of its own spacetime. But instead of forming a dead-end pit, this singularity became a conduit, a wormhole connecting to a brand new expanse of spacetime. The immense energy and matter that vanished into that black hole in the parent universe erupted here in our universe as the primordial fireball of creation. This idea elegantly sidesteps the perplexing question of what came before the Big Bang. There was no before for us because our time began with that event. But for the parent universe, it was simply the aftermath of a stellar collapse, a routine cosmic recycling on a grand scale. This paints a picture of an eternal, branching multiverse, a cosmic tree where every black hole is a potential seed for a new reality. And the implications grow even more profound. If our universe was born this way, then every black hole within it could be doing the same thing. When matter falls into a black hole here, it might not be crushed into a singularity in our own spacetime. The extreme conditions at its heart could trigger a quantum bounce, a pinching off of a new spacetime bubble that inflates into its own separate universe, forever disconnected from our own. This new baby universe could have wildly different fundamental constants. The strength of gravity, the mass of an electron, the number of spatial dimensions, all could be set randomly during this birthing process. In this vast cosmic landscape, our universe is not special or fine-tuned for life. We simply exist in one of the rare branches where the numbers came out right, allowing galaxies, stars, and planets to form. We are living proof that at least one black hole in some forgotten parent cosmos had the right conditions to spawn a universe capable of asking where it came from. These cosmic birthing events are not the only way black holes can seed the wider universe. The most powerful particles ever detected, mysterious messengers from the depths of space, might also originate from these dark giants. Ultra-high energy cosmic rays rain down on our planet, individual subatomic particles carrying as much energy as a professionally thrown baseball, all compressed into a speck smaller than an atom. For decades, their source was one of astronomy's greatest puzzles. No known process in our galaxy is violent enough to launch such projectiles. The leading theory now points a finger at the most energetic engines in the cosmos, the supermassive black holes at the hearts of active galaxies. These are not quiet monsters. They are surrounded by vast, swirling disks of superheated gas, and often they fire out colossal jets of plasma stretching for thousands of light years. It is within these chaotic, magnetized jets that the magic happens. The mechanism is a cosmic version of a particle accelerator, but on an unimaginable scale. Think of a surfer catching a wave. As a charged particle, like a proton, enters the turbulent magnetic fields within these jets, it can get caught in a wave of energy. Each time the magnetic field lines break and violently reconnect, they fling the particle forward with tremendous force. The particle surfs this series of magnetic shocks, gaining a little more speed with each bounce, traveling along the jet for millions of years until it reaches an energy that dwarfs anything we can create on Earth. Finally, it is ejected into intergalactic space like a bullet from a rifle. These particles travel for eons across the vast cosmic voids until one, by chance, slams into our atmosphere, creating a shower of secondary particles that our detectors can see. The sheer power required points directly to the gravitational dynamo of a supermassive black hole, capable of powering the universe's most potent natural accelerators. The colossal jets and radiation blasting from a supermassive black hole do more than just light up the cosmos. They may be the very architects that shape the galaxies they inhabit. For a long time, we saw these central black holes as mere residents, giant monsters lurking in the dark heart of a galaxy. But a revolutionary theory now suggests the relationship is far more intimate. The black hole and its galaxy grow up together, locked in a cosmic dance of creation and destruction. This is the co-evolution paradigm, and it places the supermassive black hole in a role of immense influence. How can a dark object that consumes light possibly help build a galaxy? The answer lies not in what it eats, but in the incredible energy it releases. As a supermassive black hole feeds, it doesn't do so quietly. It powers quasars and active galactic nuclei, some of the brightest and most energetic phenomena in the universe. The radiation and plasma jets screaming outward from its poles act as a global regulator. They pump vast amounts of energy back into the surrounding gas, the very raw material for new stars. This energy can heat the gas, preventing it from cooling down and collapsing into new stars. In some cases, the black hole's powerful winds can even blow the gas completely out of the galaxy. This might sound purely destructive, but this regulation is crucial. Without it, a galaxy would burn through its fuel too quickly in a frenzy of star birth, leaving it a barren wasteland. The black hole's furious activity prevents that, slowing down star formation and allowing for a stable, long-lived galaxy. Its gravitational pull also helps shape the galaxy's central bulge, that dense, spherical swarm of stars at the core. The black hole's mass is directly linked to the bulge's mass, a telltale sign of their shared history. They grew in lockstep, the galaxy providing the food, and the black hole providing the feedback that shaped its home. So the next time you see an image of a majestic spiral galaxy, remember that its beautiful structure, its very existence, might be governed by the dark heart beating at its center. Our most fundamental theories of physics shatter at the edge of a singularity, a division that black holes force us to confront directly. Within their deepest regions, the quantum world of the very small must finally reconcile with the gravitational realm of the very massive. This makes every black hole a potential testing ground, a natural laboratory for the long-sought theory of quantum gravity. We cannot build a particle accelerator powerful enough to probe these energies, but the universe has provided its own experiments, and we are learning to read the results. One of the most promising signals comes from the final moments of a black hole collision. When two black holes spiral inward and merge, they ring spacetime like a bell, sending out gravitational waves. The specific frequency and decay of these waves, known as the ring-down, carry the fingerprint of the new object structure. According to classical general relativity, a newly formed black hole should settle into a calm state with a smooth, predictable ring-down signature. But if spacetime is fundamentally granular at the quantum level, if it is made of discrete units, the event horizon might have a subtle texture or fuzziness. This quantum structure would alter the gravitational wave signal in a tiny but potentially detectable way. The ring-down might exhibit faint echoes or specific modifications, a slight deviation from Einstein's pure prediction that whispers of the quantum nature of gravity itself. Another signature lies in the most elusive of emissions, Hawking radiation. For a large black hole, this radiation is too cold and faint to ever be observed. But for a microscopic black hole, the final burst of evaporation would be a spectacular event, a flash of high-energy particles. The precise spectrum of that final burst, the specific energies of the particles released, would be a direct probe of the black hole's quantum structure. It could reveal whether the interior is a chaotic fuzzball, a smooth wormhole, or something even stranger. By patiently observing the echoes of colliding giants and searching the sky for the dying flash of a tiny one, we are not just studying black holes. We are attempting to listen to the quantum notes from which the symphony of spacetime is composed. This deep connection between gravity and quantum information leads us to a stunning realization. Black holes are not just gravitational monsters, they are also cosmic furnaces governed by the laws of thermodynamics. The man who first saw this link was a young graduate student named Jacob Bekenstein. He made a startling proposition that seemed to defy common sense. He argued that a black hole must possess entropy. Entropy is a measure of disorder, the number of ways you can rearrange the microscopic parts of a system without changing its overall appearance. A tidy desk has low entropy, a messy desk has high entropy. Bekenstein realized that when you throw something into a black hole, you are increasing the disorder of the universe. That object, with all its intricate information, vanishes from our sight, and the universe becomes a more disordered place because of it. The black hole must account for this loss. Its entropy, he proposed, is proportional to the surface area of its event horizon. The larger the black hole, the more surface area it has and the more disorder it can contain. This was a radical idea because if a black hole has entropy, then by the fundamental laws of thermodynamics, it must also have a temperature. But a temperature implies it must radiate energy, and everyone knew that nothing, not even heat, could escape a black hole. This is where Stephen Hawking entered the story. He initially set out to prove Einstein wrong, but his calculations led him to a shocking truth. He discovered that black holes do indeed radiate. They have a temperature and they glow with what we now call Hawking radiation. The cold, dark abyss was warm. This revelation completed the picture, forging an unbreakable link between the laws of thermodynamics, gravity, and quantum mechanics. A black hole is a thermal object. It has entropy, temperature, and it obeys the same thermodynamic rules as a hot cup of coffee or a steaming star. The profound implication is that gravity itself may be an emergent property, not a fundamental force. Just as the concept of temperature emerges from the chaotic jiggling of trillions of atoms, the force of gravity might emerge from the collective behavior of countless tiny bits of information stored on the event horizon. The immense pull of a black hole could be a thermodynamic force, a consequence of the universe's relentless drive toward disorder, playing out on the most colossal scale imaginable. The universe's most elusive black holes could be smaller than an atom. These hypothetical objects, known as microscopic black holes, would pack the mass of a mountain into a space trillions of times smaller than a grain of sand. Their existence hinges on the extreme conditions needed for their creation. One potential birthplace is not in the depths of space, but right here on Earth within our most powerful particle accelerators. When the Large Hadron Collider smashes protons together at nearly the speed of light, it concentrates an immense amount of energy into a vanishingly small point. Under the right theoretical framework, this collision could, for a fleeting instant, warp spacetime so severely that it pinches off into one of these tiny black holes. The same process is thought to occur naturally when ultra-high-energy cosmic rays slam into our atmosphere, a constant, unseen experiment conducted by the cosmos itself. The fate of such a tiny black hole is sealed almost the moment it forms. Because of its minuscule size, the effects of Hawking radiation would be extraordinarily powerful. Instead of a slow, eons-long evaporation, a microscopic black hole would vanish in a spectacular flash of radiation, lasting less than a trillionth of a second. It would be a brief, brilliant spark of existence, a blink and you miss it event. This instant evaporation is precisely what makes them so valuable to science. Detecting that final, high-energy burst would be a direct confirmation of Hawking's most famous prediction. But the implications run even deeper. For such a tiny black hole to form at the achievable energies of our colliders, the fabric of spacetime might need to be very different from what we perceive. Some theories, like string theory, suggest the existence of extra, hidden spatial dimensions. These extra dimensions could fundamentally alter the strength of gravity on the smallest scales, making it easier for a microscopic black hole to pop into existence. Therefore, finding one would not just prove Hawking radiation. It would be our first direct evidence that our universe has more than 3 spatial dimensions, unveiling a hidden architecture to reality itself. The hunt for these tiny, transient giants is a search for the fundamental pillars upon which the universe is built. These silent, dark giants may one day become the final monuments in a dying cosmos. As the universe expands over trillions upon trillions of years, stars will gradually flicker out, galaxies will disperse, and the cosmos will grow cold and dark. In this distant era of the heat death, black holes will stand as the last large, organized structures, the sole keepers of mass and energy in an increasingly empty expanse. Their immense gravity will have swept up the last remnants of stellar debris, and they will drift in the profound silence of an ever-cooling universe. Yet even they are not permanent. Through the slow, inexorable process of Hawking radiation, these last behemoths will themselves begin to fade. A supermassive black hole with the mass of a galaxy will take an almost incomprehensible length of time to evaporate, a number with over 90 zeros. But given enough time, that process will complete. One by one, these final anchors of reality will vanish in a faint, final flash of light and particles. What remains is a universe nearing its ultimate state, a thin, cold soup of subatomic particles and radiation, stretched across an infinite and ever-expanding void. The final evaporation of the last black hole marks a profound transition. It is the moment when the universe loses its last organized structure capable of holding information. With that final flash, the last bits of data about what once was, the history of stars, planets, and life, are released back into the cosmos, but into a universe so vast and dilute that the information can never be reconstructed. It is the ultimate erasure of history, a transition from a cosmos with a past to a cosmos of pure, featureless equilibrium. This is not a violent end, but a quiet fading into maximum entropy where nothing ever happens again. The story of the universe, from a fiery beginning to a dark, silent end, may be bookended by the life and death of black holes, the last storytellers in a tale of cosmic time. 25 theories, each one a key unlocking a different door in the mansion of cosmic mystery. From gateways to other universes to the holographic nature of reality, these ideas reveal that black holes are far more than simple monsters of gravity. They are cosmic engines, quantum computers, and perhaps even the seeds of new universes, forcing us to rewrite the textbooks of physics. The journey through these concepts stretches our imagination to its very limits, challenging not just what we know, but how we think about existence itself. Which of these incredible possibilities resonates most deeply with you? Do you believe our universe was born from a black hole in another reality, or do you find the elegant solution of the fuzzball more compelling? Share your thoughts in the comments below and let us know which theory you find most plausible. If your curiosity about the cosmos is as endless as a black hole's appetite, subscribe for more deep dives into the universe's greatest mysteries. Our exploration of the unknown has only just begun.